Yes, perfect. Hello everyone. Good afternoon, and thank you very much for joining this sixth and last session for this training program. Let me start by sharing my screen. For today's session, the main objective is going to be to take a deep dive, more of a focus on a specific type of machine learning techniques. But before we go into that, as promised on Wednesday's session that was cut a bit short, that I wanted to come back to the graph coloring problem in particular in order to showcase one way to handle these kind of combinatorial problems that rely on hybrids or quantum classical methods. And I also wanted to illustrate with a quick execution that is already implementable on real devices as well to showcase the potential power of these machines. So once again, as a reminder, graph coloring, or more precisely, the minimum vertex coloring problem asks you for any given graph to allocate colors, to allocate labels to each of the nodes in such a manner that the neighboring nodes, so nodes or points that are connected by edges, cannot have the same color. And you are required to do so by using the least amount of colors, the least number of labels possible. So as a quick illustration for this very, very simple graph on the left-hand side, good coloring with a minimum number of colors in this case can be seen on the right-hand side. It is indeed the minimal number of coloring because you need to use at least 3 colors due to the presence of the triangle, so that fully connected 3-node block that inhibits you from being able to use only 2 colors in any given scenario. So you know that you need to use at least 3 colors, and by using 3 colors, you can indeed color the whole graph. There are many different strategies to find good coloring or even the optimal coloring that have been developed over the past decades or even centuries, because it's a very, very old problem, one of the first graph-based combinatorial problems, actually. The difficulty is that finding the exact solution typically would require too much time, too many iterations for any given algorithm. So in a classical sense, the difficulty class of this problem is considered one of the harder problems, falling into a complete complexity class in particular. So the more nodes you have and the more connected the nodes you have, the more difficult it becomes in general. For this reason, people have been coming up with different strategies to try to simplify the problem, to try to isolate the main technical bottleneck, the main complexity of the problem. And one such strategy is what we call a column generation based approach. So in combinatorial optimization, it is quite a powerful tool to use decomposition techniques in order to separate your main problem into multiple sub-problems that communicate with each other in order to provide a solution for the original problem by solving these subtasks, these sub-problems in a sense. The column generation in particular relies on the primal dual formulation of any type of optimization problem. in order to propose what we call a master problem or reduced master problem, which tasks you to solve the initial problem, but in a simplified context, typically only allowing for the graph coloring a specific type of coloring or a specific number of colors to be used. And behind it, there is a second problem, what we call a sub-problem, that is tasked with generating new scenarios, generating new types of instances in order to enrich the master problem itself. So the main idea behind this type of decomposition technique is illustrated in the bottom half. So you have on the left the master problem or reduced master problem that is tasked in solving the minimum vertex coloring problem, but on a limited type of scenarios, so that you are not facing combinatorial explosion. You don't have to test all the different types of colorings. You are very restricted in what type of colorings you are testing. And you have the sub-problem that is tasked in identifying new strategies, new instances of coloring in order to enrich the master problem. With this, the master problem itself becomes rather easy because you are limiting the search space to find a solution. The complexity, the hardness of the problem, therefore, becomes on how to generate these new meaningful instances, so how to efficiently solve the sub-problem. Depending on the type of problem you are dealing with, such decomposition techniques can lead to problem formulations in which the sub-problem is as difficult to solve as the initial problem. So in a complexity sense, you do not gain anything. However, this decomposition can lead to reduced instance sizes or reduced number of constraints in the optimization formulation, for instance. With this, you can make the problem, for example, compatible to be executed on a quantum computer by reducing the size or certain other parameters for the subproblem. So in this particular instance, for the graph coloring itself, the subproblem itself relies on identifying nodes that can be colored with the same color. Meaning that we are trying to identify a set of nodes that are not connected with each other. Because if they are not connected with each other, that means that they can adopt the same coloring. But if you remember, a set of nodes that's not connected in between themselves is called an independent set. And we have seen that we can construct some quite efficient methods to find independent sets, and more specifically, find large independent sets, if you're lucky, even maximum independent sets. Herein lies the potential of incorporating a quantum component instead of relying on classical generation of these independent sets in this new information for the master problem, which is typically limited in what type of scenario it can propose. The main advantage for a quantum-based implementation is that natively, naturally, it can propose multiple good scenarios, since quantum information itself has a probabilistic notion associated to it. So the information a quantum component generates is inherently probabilistic. Therefore, what it would propose to enrich the solution is naturally not just one new solution candidate, but can be many solution candidates at the same time. This fact can accelerate the convergence, can accelerate the performance of the algorithm itself. Put it in a different way in order to schematically represent how such a hybrid column generation method in particular can look like for an execution on a graph coloring based problem. We have the master problem, the reduced master problem, also called the RMP. So reduced master problem, which is tasked by solving the minimum vertex coloring on a limited amount of information. So for specific types of colorings allowed. In the initial step, you only task it to color the graph with as many colors as there are nodes. So the solution becomes trivial, and that's typically a good starting point. So the master problem is tasked in finding a solution for the coloring problem, but in a very, very limited search space, in a restricted types of potential solution candidates. This is typically something that can very easily be checked by classical computational resources because you are just solving some linear systems of equations behind the scenes. Behind that, there is a subproblem, what's typically called a pricing subproblem, that is tasked with identifying new scenarios, identifying new colorings that allow the reduced master problem to find a better quality solution. So typically identifying nodes that can be colored with the same color in order to reduce the amount of colors the master problem needs to use to solve the instance. Therefore, if it's done quite efficiently at each iteration step, the pricing subproblem can reduce the amount of colors necessary by at least one. If you are relying on a quantum computer, it is also possible to take multiple steps at the same time and reduce the amount of colors necessary from the number of nodes all the way to multiple instances at the same time. So it can potentially be quite a powerful tool depending on how well you manage to extract these new scenarios, which is typically dependent on the graph as well as on the implementation for the pricing subproblem. And now what I wanted to illustrate is this method in action. So implemented very simply on Pulsar using some built-in graph modules to generate a quick instance for it. Again, so we are tasked in building a master problem who is supposed to find the right graph coloring based on a limited number of scenarios to be tested. And we are building with Pulsar the quantum component to identify new scenarios, in this case, to find large independent sets with some extra considerations in order to ensure a good convergence. So as you have seen, there is a communication between the master problem and the subproblem itself. The communication is ensured by, once you solve the master problem itself, its solution is taken into consideration to generate new independent sets, and the new independent sets are enriching the search space of the master problem to find an even better solution. So the communication really goes both ways. To illustrate how it works in a more step-by-step approach, as I mentioned, you initialize the problem by finding a good initial coloring. A nice starting point can be to just simply use as many colors as there are nodes, because in that case, the solution itself is trivial. The master problem, so the reduced master problem itself is solving the graph coloring problem based on combinatorial form where you can associate variables to nodes and write it in more precise mathematical form. And you can use the primal dual formulation to associate constraints, associate inequalities based on the obtained initial solution itself. Then you use this information, so you use the information on the generated solution in order to generate an instance for the pricing subproblem. So you really use the solution obtained by the master problem to generate a version of the subproblem, which is typically a variant of the initial graph with some additional penalty terms. These penalty terms ensure that your convergence will head to the right direction. why you need these penalty terms. This is something that will be illustrated once we tackle our example. So in the execution, I have generated this 6-node graph, which is a very, very simple graph that has a particular quirk. The particular quirk of this graph is that when you try to do a minimum vertex coloring, the optimal solution, as we will see, is to color the graph with 3 different colors. So the optimal coloring will correspond to allocating a color to each of the nodes of the large triangle and the opposing node in the middle of the edge of the large triangle. With this, you can allocate with 3 colors good coloring. Why is this quirky graph? It's because that if you look at this graph from a maximum independent set approach, you can see that the 3 outer nodes, so the 3 points of the large triangle, form a maximum independent set, and they form the maximum independent set of the problem. However, if you were to choose this coloring and use this maximum independent set to use for the starting point of the coloring, so if you were to color these 3 outer nodes with the same color, that would imply that the 3 inner nodes would need to be colored by different colors by 3 other different colors because they form a triangle, so maximally connected subset. So you cannot use the same color or any of the 2, and any of them is connected to one of the outer nodes. So if you were to rely on the actual maximum independent set of this graph to try to find the coloring, you would end up with a suboptimal solution that would need to use 4 colors in total. But you can do better coloring if you only select the opposing nodes as independent sets. And here lies the power of constructing a good quality independent set generator. And what we have seen with the adiabatic approach previously is that for neutral atom system, you can tailor the experience to favor the actual maximum independent set or to select different independent sets that are close to the maximal independent set. So they are not maximum independent set, but they are maximal in a sense that they cannot be extended. So you can really tailor your independent set generator to favor large independent sets without actually pushing for the maximum independent set solution, which in this graph's case, in this scenario, can be not the best solution. And what it looks like in actuality, so we are doing it in an iterative fashion. At each point and each section, I'm generating an atomic layout for my graph. So in the initial step, I have all 6 of my atoms formed corresponding to the graph itself. And I have a specific adiabatic pulse that I expose this atomic register in for me to find large independent sets. So naturally, as we have seen, it will generate multiple independent sets with specific probabilities, and we can rely on these probabilities to enrich the maximal, the master problem itself in order to try to construct a new coloring. And based on that, what I'm doing then is I'm reducing the graph itself. So as a next iteration, I'm eliminating one of the independent sets that I've chosen for with the right coloring, eliminating the right one with the right weight, so that I've eliminated 2 of the nodes, 2 and 4, 2 of the outer nodes, which was an independent set solution, not the maximum independent set, but an independent set solution. And I'm solving once again the independent set selection to find a new good coloring for it. And with that, in just 2 iterations, I am able to select the right coloring for this graph. As you can see, with 3 colors for the opposing nodes. It managed to allocate the right colors, all the while avoiding the pitfall of selecting the maximum independent set in the initial scenario. I just wanted to showcase this in order to illustrate that greedy methods can be dangerous. Maximum independent sets might not be the best scenario, especially for these more complex problems as a subtask. Therefore, being able to rely on the quantum component that is able to identify large independent sets without necessarily favoring the maximum independent set can be a very, very powerful tool to avoid potentially worse quality solutions. So I just wanted to add this to complete on Wednesday's session. Are there any initial questions about this section before we tackle today's topic and machine learning? If not, you can still ask later, or it's not a problem. We can come back to this. So let's move on to today's theme, which is going to be around machine learning, around more specifically quantum machine learning. And we are going to focus on a specific type of machine learning methods and called graph machine learning methods. The reason for this is, as we have illustrated, neutral atoms type systems are particularly adept at handling graphs. By default, unit disk graphs, so graphs in which edges are drawn based on a distance or threshold for a distance, but with graph embedding techniques, larger classes, larger families of graphs can become accessible as well. In any case, the mathematical representation of the atomic register itself lends well to graph-based formulation, and we can find graph structures within many different machine learning approaches, actually. So in order to start, let's quickly take a look at what is machine learning about and what is quantum machine learning about. So when we talk about quantum machine learning in general, it typically is built upon the 2 main components present. So we have the component of the data itself that's coming from some kind of source. We have a machine learning model, so this tool that is there to learn from this data in order to extract results. And on this schematic representation, we are inserting a quantum layer at some point. You have different choices in selecting where you want to insert exactly this quantum layer. This can be something that's closer or in relationship with the data part of it, or this is something that can be integrated inside the machine learning model. To give you a better visual and a better understanding, we can sort of distinguish 4 different scenarios in this sense. So this is represented on the bottom half, separating the data and the model itself and its nature. So we can talk about data that's coming from a classical source and data that's coming from a quantum source. So data can be naturally quantum. For instance, you can think about any kind of quantum sensors. So there are quite a few different quantum sensors available that naturally generate quantum information as their initial data that can be rather challenging to be processed, but it can be processed by both classical and quantum reinforced methods as well. So therein lies the separation, and that's why you can distinguish 4 different scenarios. So the easiest and the most well-known that we have been already dealing with is handling classical data with classical processing power. With the rise of quantum sensors for the past couple of decades, there have been more and more methods that were tackled in integrating quantum data or quantum-based data into their existing classical machine learning approach. So that is the bottom left part of the screen, where the model is tasked in learning from quantum data, or at least from the measurements made on quantum data, because classical components cannot efficiently handle all the complexity of quantum data. On the other hand, and more recent investigations are focusing on incorporating a quantum element, a quantum layer, on the machine learning model, on the processing side, that can once again tackle classical data. This is how we typically test different quantum machine learning models, or it can also tackle quantum-based data as well. What's interesting to observe and to keep in mind is that even when we are handling quantum-based data with a quantum-based machine learning method, there is still a classical component associated to the optimization side that is not performed on the quantum computational resource. The reason for this is that if this optimization cycle is much better to be executed on a classical computer, or simply on classical computers with this linear algebraic optimization type tasks are much better performing than the current capabilities of quantum computers at the very least. So in the foreseeable future, there will always be some kind of classical component associated to this, which is related to the optimization part of the machine learning model itself. The optimization relates to how the model itself is learning. So this implies some kind of convergence, and for this convergence, to guarantee this kind of convergence so that your model is becoming better and better at each learning cycle, this typically relies on a lot of arithmetics and a lot of linear algebraic operations, so matrix-based operations or tensor-based operations, depending on the formulation, that can reach quite large system sizes that are not yet tractable with a quantum computer. So it's interesting and important to keep in mind that even with the most quantum version of quantum machine learning process, there is still a classical component involved in the optimization cycle. With that said, there are quite a few different machine learning methods out there that have a quantum enhanced variant. So here, thanks to Olivier Ezrati's report, I have listed, I would say, quite a few of the most well-known machine learning models in which you can potentially incorporate a quantum layer. So here we are talking about the side of the chart where we are putting using either a classical or a quantum element in the processing side of it. So you can see quite a few potentially familiar methods from various regression type methods, support vector machines favored by mathematicians, but towards the bottom there are quite a few neural network based architectures as well. So what this chart does, it illustrates the best known complexity of these machine learning methods in terms of how well it scales in terms of execution time as a function of the number of variables. So this is typically how we identify how complicated it is to use and to solve these models. And it compares to what is known, if it's known, what's the complexity in terms of using the quantum variant of it. So how it scales as a function of the variables for the execution time using the quantum enhanced version of the same algorithm. So what we are typically looking for is an exponential increase between the two timescales. So these are typically the best candidates where we can actually see some meaningful and important scale up in the methods. So there are quite a few examples, like for the regression models, you go from linear or polynomial to logarithmic. That's an exponential scale up. For support vector machines, similarly, go from polynomial to logarithmic. And also, interestingly, for some neural network-based approaches, you go from linear scaling to logarithmic or polynomial logarithmic scaling. Typically, we are interested in looking for methods that offer this exponential scale up because very, very quickly with the system size, you can potentially see a difference. However, what this chart also does is to indicate on additional information. In this case, does the quantum method require storing information? So is there a notion of quantum memory involved in it? Because if a method relies on being able to store quantum information, this pushes back the actual feasibility, because as of today, there are no proper ways to store reliably quantum information. Therefore, these methods, while they can promise potential exponential scale up, in terms of implementability, you will run into the actual problem of not being able to execute it properly due to the fact that you are unable to store quantum information. So as you can see, the regression models and support vector machines and quite a few of the kernel methods in actuality do rely on the fact that you are able to store quantum information to be used later, typically for the inference itself. And this poses an actual issue that you cannot efficiently implement these methods, at least not with the current state of advancement. Nevertheless, they do provide, from an algorithmic perspective, an exponential scale up, so the methods stay interesting. It's just that it's worth keeping in mind that just because from an algorithmic perspective, it's said to be faster, more efficient, does not actually imply that it will be more efficient because there can be some underlying factors to it. In this sense, neural networks, quantum enhanced neural networks have the advantage of not relying on storing quantum information. However, as you might know, there are other bottlenecks associated to them because, for instance, for a convolutional neural network architecture, it typically tends to rely on very, very deep circuits. So the error rates themselves on manipulations on physical qubits come into play very, very quickly, which can inhibit its function. So for now, the main message is that there is no perfect quantum machine learning method. There are quite a few promising ones in terms of algorithmic scaling, but typically most of them have some limitations due to the current state of advancement of the physical devices themselves, be it a lack of memory or a lack of precision required for an efficient execution. With that said, I wanted to illustrate a couple of methods in a bit more detail to explain how they work in principle and how you can incorporate a quantum component in it. One of the first examples that has arisen as a potential application of quantum computing within the machine learning field was based on kernel methods. So quantum kernel methods initially were envisioned as part of the support vector machine architecture back in the 2000s. So more specifically, the first method that came up with this was released in 2009. Back in the day when we were not yet in the full-blown artificial intelligence and large language models era. Support vector machines and kernel methods in general had a very, very good reputation, and they still have a good reputation due to the fact that they are mathematically well understood. So you can explain with proper mathematical techniques, you can prove how the machine is reaching a specific decision. And this is a major key factor in evaluating machine learning methods, being able to mathematically justify the reasoning behind it, because this then allows for you to measure properly the error, the inaccuracy, and other performance metrics, as opposed to other methods we are going to discuss later. This is a key differentiator. Nevertheless, in actual applications, these methods have been underperforming, well, except for specific domains. So one typical example is image classification, especially large image classification, where kernel methods still have viability. We are really thinking about satellite-based screening and image recognition type activities, where these methods can be very robust and powerful tools. There are a couple of other examples within which kernel methods can find an actual practical use. Other than that, they have been relegated to more of a mathematical toy example to illustrate basic principles of machine learning tools and models. These kernel methods always rely on the fact that you need to construct some kind of function. This is typically related to the kernel function itself that sends your initial data into a new, typically higher dimensional space. So in a sense, you're creating a new representation of your data. And due to this new representation of your data, you can potentially perform your prediction, your classification, your clustering task more efficiently. So it, in a sense, it incorporates and realizes a new representation of your data that's more efficient for the task you want to perform. For quantum kernel methods, you add an extra layer to this abstraction by sending your data representation in a quantum information space, so a much larger dimensional space, and then you are projecting it back due to specific measurements in a slightly different space. And this transition through the quantum space is what creates a potentially much more efficient representation. Once again, both these transitions can be exactly described by mathematical functions, mathematical operators in particular. Therefore, the error rates, the performance metrics are exactly quantifiable. Another large track of machine learning methods focus on neural networks. So a typical example is building a quantum layer on top of a convolutional neural network, but it's not the only potential example. So a neural network is nothing else but a layered architecture of consecutive machine learning models or machine learning tools that initiate with data abstraction, then rework the information in order to extract useful parts of it, mimicking or simulating how neurons in your brain would take in information and transfer information in between them. They always have a layered architecture that can be mathematically represented by a large graph. Hence, the interest in potentially neutral atoms type systems that can encode at least parts of this architecture. We are really dealing with large graph representations for neural networks. So it's not feasible to encode the whole graph in quantum systems. What people typically focus is on selecting a layer of the machine learning of the neural network architecture so a specific segment of it, and replacing that segment with a quantum computing with a layer that can be executed on a quantum computer. This can be quantum circuit representation, so a quantum logic gate-based implementation, as it is illustrated here on the image, but this can also be done using more analog considerations. Again, the main idea is you are taking one of the layers of the neural network and replace it with a different formulation that can be encoded using quantum computers. The idea is that typically you want to select one of the layers that are on the top of the architecture. So you want to keep your quantum layer close to the data so that your quantum computer still sees the data itself and is not tasked in intervening when you're doing more linear algebraic manipulations, which is typically the case in the middle layers, the mixing layers of the neural network itself. However, as I mentioned, neural networks fall into the category of machine learning models that are not mathematically expressible. So you cannot exactly represent the whole model with mathematical tools. You can understand simpler architectures, but much larger models lack this mathematical justification. Therefore, properly measuring the errors and the performances can be an issue. And this is for this reason that from a complexity theory perspective, their exact classification is still not known. And this is for this reason that it's quite hard to establish what's the actual impact of putting a quantum layer on top of the architecture, because even classically, there are many things that are not yet understood. Nevertheless, what we have seen, especially recently with large language models, for instance, that is a typical example of specific architecture of neural networks that is being used, for instance, with ChatGPT and other similar tools. What we have seen is that they have proven to be performing very, very well in industrial scale problems, learning and tackling actual real data quite efficiently. So despite the lack of mathematical evidence on why they are performing so well, they have been proven to perform so well. So there is caution from the scientific world that's issued that since the tools are not super well understood, it can be quite dangerous to rely on them. But their proven performance is really pushing the world for using more and more these type of architectures. Hence, the investigations on how you can improve the results or how we can make the results much more expressive by potentially integrating a quantum layer on the architecture. This might not help from a mathematics perspective, but it can have a lot of practicalities. Building on top of that, there is a third type of method that I wanted to illustrate, which is generative modeling, particularly important machine learning tool that has been deployed in quite a few large language model architectures, for instance. So generative modeling in essence is nothing else but taking your data and looking at it from a probabilistic perspective. So you consider your data following some kind of quite complex probability distribution, and your model is tasked by generating instances, generating samples that follow a similar or ideally the same probability distribution behind the scenes. So generative modeling, as the name implies, is tasked with generating new samples, enriching your data set, all the while keeping the main characteristics of your initial data set. A typical example is illustrated on the bottom left side, in which you can see pictures of horses, which need to be encoded to understand what these images are about. And then the model itself is tasked in generating yet new pictures of horses and only just horses. Typical realization of this, so an actual implementation relies on what we call a GAN method. So GAN stands for Generative Adversarial Networks, which is a type of strategy that has two components. And the first component is the generator itself. So the generator is tasked with creating samples, creating instances, and a discriminator, which is tasked with identifying if the generated sample fits your initial data set or not. These two components can be separately implemented in various different ways. Herein lies the element of potentially quantum, to incorporate quantum in the generative adversarial network, be it on the generator side to generate and to learn from the underlying probability distribution, or on the discriminator side to determine, based on probability distributions, whether a certain sample fits the training data or not. This is just one way to realize generative modeling, and there are quite a few others. And I wanted to cite one that's important to know about because it's showing a lot of promise recently, which is quantum circuit-borne machines, or born machines in general, which are really methods that are inherently quantum, because they rely on the probabilistic representation, the probabilistic notion of quantum information. So what they are technically doing is that they are extracting probability distributions by means of quantum wave functions or quantum states from your data set directly. And then you, by the way of measuring, simply measuring, you can create new samples from this quantum state directly. In practice, these methods tend to work quite well for discrete distributions in particular, since the measurement itself is generating a discrete probability distribution based on the number of shots typically. But there are more recent investigations that try to push these methods towards semi-continuous probability distribution functions as well. With that said, I wanted to focus for today's session a little bit more on a specific type of machine learning methods called graph machine learning methods. So far, I tried to give you different examples on different types of machine learning models that can be enriched by incorporating a quantum component. And now we are going to focus on methods and that are particularly adapted for neutral atoms type implementation. You can see there is a question. So can quantum circuits satisfy the universal approximation theorem in machine learning? To be completely honest, I'm not sure. I would say it's quite unlikely, but I need to check and verify. I'm not 100% sure, but I would say no. So for graph machine learning techniques, oh, there is one more question. Okay, so let's wait a little bit more if there are other questions coming. Yes, yes. So especially with current quantum machine learning tools, and there is always a hybrid element to it. So as I alluded when I presented the different methods, there was always a classical component that typically manifests in the optimization cycle itself. But as of today, no quantum machine learning method is purely quantum in this sense. So there is always a classical component, either directly visible or hidden in one of the subroutines of the method itself. This is something that is expected to evolve and to change, but depending on method, there are different factors that need to be satisfied in order to be able to move the methods fully on a quantum scale. So yes, for now, all quantum machine learning methods are inherently hybrid methods. So, as I was saying, I wanted to focus a little bit more on graph machine learning tools. The reason for this is from a quantum perspective, as I mentioned, graph-based tools lend well for a neutral atoms based system and its considerations. But even from a classical perspective, in recent years, we have seen an increase in interest and applicability for graph-based considerations in various machine learning methods or machine learning tools. So here I've listed a couple of examples, a couple of classical and known machine learning tools that leverage graph combinatorial techniques or graph structural techniques for their functioning itself. As I mentioned, neural networks themselves incorporate a large graph structure, but depending on the type of neural network, certain types of neural networks lend particular well in a fully graph-based implementation. Such examples are, for instance, recurrent neural networks that have a directed graph representation in particular, but there are actually graph-based neural networks in which the neurons themselves are represented by smaller portions of graphs, or in which case they are particularly adapted to learning and handling graph-based data sets. So deploying specific neural network architectures on network analysis, so from telecommunications, from supply chain management, and such. So different neural networks can be particularly adapted to admitting a graph-based representation on the different components themselves, not just the structure as a whole. And therefore, using techniques from graph theory, you can infer and leverage certain properties of these graphs to improve the performance and the architecture. Another such example is graph attention models, which is a relatively new and particular tool that has proven to be quite efficient in handling specific types of classification tasks in particular. Typically, graph-based structures are quite adept at encoding relationships, so encoding and understanding connections either between the data set or between extracted information from the data set. And this is what we are going to leverage with the method that I'm about to present. So the method in particular is called quantum evolution kernel. This has been developed by our Pasqal scientists. So you have quite a few publications associated to it. And it is inherently a method that relies on the native capabilities of a neutral atom system to encode graphs. And the tool itself builds upon this in order to extract information from graphs and then pass on this extracted information for more conventional classical machine learning methods in order to improve the overall performance. So this is one of the examples of a quantum machine learning method in which the quantum layer is actually close to the data itself because the technique inherently relies on reinforcing the information extraction part, especially for graph-based datasets that are classically quite difficult to be handled. So what I wanted to illustrate is that graph-based datasets, so network-based datasets, are present in all walks of life, in various different scenarios and industrial fields, from energy industry, so electricity grids, or gas networks, or water distribution networks, in financial systems, modeling transactions, describing portfolios, all the way to the pharmaceutical industry, for instance, considering medications or describing molecules. When you draw molecules, you are drawing a graph structure in a sense, as well as in transportation and logistics, you are dealing with network-based data sets all the time. The issue is that graph-based or network-based data is inherently complicated to be efficiently understood by classical methods because simply a classical way of representing data is quite adept at describing on a coordinate basis. However, when you need to incorporate relations, so you need to not only allocate nodes but edges as well, there it complexifies quite heavily the way you could represent this data. So what we are essentially doing with neutral atoms quantum computer, so this is really leveraging the fact that you can represent graphs in the atomic register of neutral atom system. So it's particular to this technology or to technologies that have this flexible implementation, this flexible architecture. And from the graph itself, we construct specific target Hamiltonians. So what we do is we start exciting the graph representation in a specific way, in a specific alternating or iterative way, in order to generate a probability distribution. So to generate some kind of excited state associated to the whole graph. And these excited states will have a probabilistic notion, as is the case for any quantum method. And this probability distribution, this distribution of bit strings, the distribution of excited states, will form what we can consider a trace, a footprint of your graph. So you are using your quantum method to encode the graph, excite the system in a strategic way in order to create a probability distribution that is specific, that is representative of your graph. Once you have this probability distribution, you can extract this for any instances of a graph, so for many different graphs, and you can use these probability distributions as the actual information you would need to handle to generate different methods to train machine learning models. In particular, in this case, we are leveraging kernel methods that can be quite efficiently trained based on the probability distribution itself. So basically, you are abstracting from the graph structure to a probability distribution in order to find a better representation that is much more compatible with specific machine learning tools, and therefore you can increase the performance of the overall model itself. Viewed in a different fashion, as I mentioned, we are tasked in associating from a graph structure some kind of probability distribution, some kind of trace, a footprint of the graph itself. Typically, from a classical point of view, this is the heart part. This is the hard problem to be done to associate this, to extract information from graphs themselves, to extract meaningful information from graphs themselves. And therein lies the potential of the quantum component, in particular for a neutral atom-based system, is that you can quite efficiently associate to a given graph various different probability distributions, depending on what kind of evolution you instill on the graph. Typically, what you want to achieve is you want to excite the system in order for entanglement to manifest. So if you send sufficient energy to your system, this will start exciting all your atoms, which will instill natural selections. So certain atoms can reach high energy states, while others are pushed to lower energy rates. This was the Rydberg blockade phenomena. We were using this, for instance, to be able to select independent sets on a graph. You are trying to leverage this, but in an iterative alternative fashion in order for the final state, the final energy state that you reach with your Hamiltonian simulation to be representative of the different connections. So you want to instill enough excitation so that your final result, so the bit strings with their probabilities have some inherent meaning associated to how the nodes were connected. Because for us, connected nodes imply that the atoms can interact with each other, so there is a possibility of entanglement. Therefore, if you can instill sufficient amount of interactions, the probability distribution you extract, so the bit strings you extract, will be a good enough representation of which nodes, which bits of the bit string were actually connected with each other. And that's what we are trying to achieve in creating this probability distribution-based footprint. Once you have this available, you can use it to formulate a kernel, to formulate this mapping that you can use to perform different tasks. You can use it to classify the data. You can use it to make even predictions for new inference for new data points as well. The additional advantage is that once you have these generated probability distributions, you can directly construct the kernel itself, which is going to be a combination of probability distributions concatenated and compiled into a specific matrix form. And therefore, the tool itself will be detached from the quantum component, strictly speaking. So you are really using the quantum element to extract the information, and you no longer need to leverage it afterwards for training the model itself. However, you will still be reliant for the inference on the quantum element because you need to be able to generate a new probability distribution for a new data point for it to be understood by the machine learning model. For this specific technique, as I mentioned, there is an inherent advantage to encode it on a neutral atoms based on an analog system in particular, because you can leverage the flexibility of the positioning and you can leverage the continuous in time evolution in order to instill a meaningful information extraction. However, you can create a representation using digital, so quantum logic gate-based executions as well. The particularity of a quantum logic gate-based information extraction is that digital quantum computers or fixed architecture quantum computers in particular cannot directly encode the graph itself, so they need to work with a representation of the graph. This representation typically involves what we call the adjacency matrix. So for your graph, you associate a matrix that indicates which nodes are connected with which other nodes. However, the issue with this is that this matrix representation depends on how you have labeled your graph, how you have designated the different nodes. So what you can see here as an example is I have the same graph 3 times, but I have indexed the nodes in 3 different ways. And due to this, the allocated matrix, the associated adjacency matrix, is different. Therefore, if you're reliant on this matrix representation, which is not unique, the type of implementation you would get from a quantum circuit-based representation, which needs this matrix form in order to try to encode it using the quantum logic gates, can give quite different footprints, quite different labels, quite different quantum circuits for it to be understood, even though inherently you were dealing with the same graph. So there is a natural advantage for using an analog neutral atoms-based implementation. However, it is not prohibitive. You can still rely on other techniques to use other implementations. By the way, this association of a graph with its adjacency matrix is what is typically being used in a classical sense as well. And as you can see, since the representation is not unique, it depends on how you have labeled your graph. Therefore, for a single graph, you can associate many different adjacency matrices. So this can complicate things for a machine learning model that needs to rely on these matrix representations, because all these matrices should be understood the same way. I see there are a couple of questions. So graph coloring was used for telecommunications to have efficient frequency use. For example, it can be used also for allocating the antenna, positioning the antenna, or you can also complexify the problem itself by adding additional constraints. So I showed the simplest example, but there are many different layers that you can add on top of that. So for graph machine learning, so nodes are associated to quantum bits, and you can use superposition and entanglement to represent various types of data in the same condition. So this is true for both approaches. Both for the graph coloring and for these graph machine learning methods, since you rely on the fact that you encode the graph within the neutral atom system, so you associate nodes to quantum bits, you can potentially store more information than just the position or a single value. You have 2 degrees of freedom. More than that, typical graph representations may not have distance as part of their component. So you can use the distance between the atoms as an extra degree of freedom to some extent to encode additional data. And all this data encoded into the graph representation can then be leveraged by the quantum component in the optimizer to solve efficiently an optimization problem for not just frequency allocation, but for other considerations, or to better understand from a machine learning perspective. So indeed, you can design quite complex interpretations and algorithmic representations, leveraging the fact that you are encoding graphs using qubits, and you have access to multiple degrees of freedom technically. So both tools, both on the optimization side and the machine learning side, rely on the fact that you are encoding your graph within the atomic register. Therefore, you can make use of the full potential of this encoding for the problem formulation. So for graph encoding, you can make use of both channels actually to create different footprints for your graph to create different probability distributions. It's still privileged for the Rydberg channel due to the fact that in your probability distribution, so in the bit strings you want to generate, you want to somehow have it manifested how each of the nodes are connected. So you want to excite your system in order to create entanglement, which can only be done by the Rydberg channel. and then you want this entanglement to manifest in your bit string distribution. So I would say that there is a privilege, or there is a preference, I should say, for the Rydberg channel for this reason, that you want to excite your graph representation in order for the connections to manifest themselves in the bit strings after the measurement. Yes, one more question. I'm not sure what you mean by making the representation lower exactly. Well, you rely on the Rydberg blockade for the entanglement itself to manifest. That's how you can create different scenarios. That's how you can have the probabilistic notion itself appear. So if I have the Rydberg blockade, for instance, in this graph that appears between nodes 1 and 2, what I will see is that in half the instances, it will be the node 1 that has the 1 information, and in half the instances, it will be the node 2 that will have the 1 information. So in my probability distribution, this part will manifest as sort of an alternating bit string. So I will have a trace in my probability distribution that captures the fact that nodes 1 and 2 were connected due to the Rydberg blockade. So for me, that's a positive thing because I have information on the connections that are manifested on the bit string representations. Once again, you are extracting probability distribution, a discrete probability distribution following a couple hundred executions, a couple hundred shots. And you are reliant on the fact that for different shots, the bit strings will be different based on which parts became entangled and how the Rydberg blockade actually manifested. So for me, you want to observe the Rydberg blockade. You want to observe the entanglement between the atoms in order to create this discrete probability distribution that encapsulates the fact that there were connections between certain nodes. Yes. So the idea is really you want to create this discrete probability distribution that's really informative of the graph structure. So you're really looking at the graph from a structural point of view. Nevertheless, so there is sense in involving the Raman channel as well. So to have some local interactions, but then you would need to rely on encoding information different way on the graph. So that's a viable route as well. But here the accent is really on how to capture the connections in the graph, because that's the hard part to model classically. So if you look at it from a data perspective, encoding the nodes themselves is the easy part. You can use one parameter, you can use different coordinates, you can use 10 variables to encode each of the nodes. You can do that classically. The hard part is how to manifest the connections, how to manifest the links in your data. And for that reason, the excitation can be much more useful. With that said, I wanted to illustrate this method, this graph kernel method, the quantum evolution kernel, with a specific example that's coming from the pharmaceutical industry. In order to get there, I first a quick highlight on the different quantum machine learning methods that are being developed for neutral atoms type systems. So in today's sessions, we were focusing on the quantum evolution kernel. So how to extract efficiently information from graph-based data that then you can use with conventional machine learning processing tools to enhance the overall performance. But that's not the only way to move forward with neutral atom systems. There are quite a few other tools that can be featured and can be investigated that lend quite well for neutral atoms-based implementations. So here I just wanted to give quick outreach to methods based on neural networks that we have been developing, for example, that can be used to solve differential equations, that can be used to do generative modeling that I have illustrated previously, and that can also be used to perform various optimization tasks themselves. So neural networks can be quite flexible tools depending on how well you have chosen the quantum layer, typically the convolutional layer of the architecture. They can be adapted to various different scenarios. So for today's session, we are not going to go deeper than that in this side. I just wanted to mention that there are other potential topics that can be looked at in much more details. And I invite you wholeheartedly to take a closer look to these other methods as well. And the advantage is that, for instance, if you start working with the Cadence software tool, so that features a lot of compatibilities and integration with existing Python-based machine learning tools that allow you for quite efficient quantum neural network implementations, even locally on your own computer. So you can investigate and start developing for the neural networks as well using the Cadence tool if you're interested. With that said, I wanted to illustrate the practicality of the quantum evolution kernel. So to better understand graph-based datasets with a particular problem that actually comes from industry. So I've alluded to this previously, that graph structures and graph-based data can appear in various different scenarios, and the pharmaceutical industry or chemistry in particular is not an exception. So whenever you're dealing with molecules or molecular compounds, the geometric representation of said molecules, so typically how you will draw the molecules themselves, is actually a graph representation of the actual molecule. Typically, how you draw them, especially for smaller molecules, is you're considering two-dimensional structures. In actuality, for larger molecules, especially, we are dealing with three-dimensional structures. Therefore, there is an initial consideration on how to represent efficiently a three-dimensional graph structure on a two-dimensional plane. But for now, we are going to focus on smaller molecules that can be effectively represented on a two-dimensional plane, so with simple graph representations. The idea here is that whenever you are developing new medications, there is an inherently complex procedure involved in trying to identify which molecular compounds and which molecular families can potentially instill the desired reaction, because for a medication, you want to target proteins, you want to target specific molecules in your body in order to fix its misbehavior, typically when you're sick or when you're observing some kind of altercations. For this reason, developing new drugs can take quite a lot of time, because identifying which molecules, which molecular compounds could potentially have the desired effect can take years due to laboratory experiments. So you need extensive testing before medication can appear actually on the market. So especially handling new types of diseases that pop up, it's key to reduce this development procedure as much as possible. For this reason, in recent years, machine learning and artificial intelligence tools have been increasingly mobilized in order to try to shortlist, try to cut down this identification process by trying to identify good types of molecular compounds, good distribution of different molecular compounds that can potentially have the desired effect. In actuality, what is typically being done is that for drug discovery in particular, they use various sets of machine learning models to make predictions on larger and larger families of molecules in order to try to shortlist candidates and try to reduce the number of molecular compounds that need to be synthesized and tested in a laboratory experiment as much as possible. These techniques have proven quite efficient, but still they can be quite time-consuming because they typically rely on a lot of quantum chemical or molecular computations to train, to create the models themselves. So if you can bypass this computation-intense part by creating more efficient models, you can cut down the training time by quite a considerable factor. And herein lies the potential of the presented quantum evolution kernel method, which does not perform any kind of chemical computations in and of itself. What it does, because it's a graph machine learning tool, it really just looks at the molecule, looks at the geometry of the molecule, and extracts the footprint, the aforementioned probability distribution associated to the geometry of the molecule, and then you use this geometric footprint to try to learn and understand its behavior. This seems like a rather simplification if you bypass most of the chemical computations that you might not end up with good results. But in actuality, it's quite the opposite. So when the method initially appeared, we did quite an extensive investigation on a specific data set that targeted different molecular compounds, and it was a classification task aimed at trying to identify which molecular compounds can instill a toxic reaction within a certain species of lab rat, and which molecules are safe for ingestion for that specific lab rat. So it's quite an extensive data set that's publicly available on which we did different investigations in order to determine how efficiently we can predict this toxicity on the different molecules. And so what we did is we trained different models involving the quantum evolution kernel and other known methods in order to compare the precision, the accuracy of the classification itself. And what we have found is that it's quite comparable to a lot of the currently deployed and scientifically referenced methods. In certain cases, it can even perform better due to this enhanced data encoding capability, so the enhanced information extraction from the molecules themselves. To get a bit more visual illustration, so once you have your graph representation of the molecule, as I mentioned, you expose it to a sequence of pulses in order to extract probability distributions. And typically, these probability distributions can take various different forms, and you want to rely on these probability distributions in order to identify and separate the different molecules from each other. So this manifestation is quite visible for these two quite different graph structures, which behave and which therefore evolve in quite a separate fashion in time because of the fact that their structure is quite different. What we have seen in particular is that encoding efficiently the graph itself on a neutral atom system is already key, and we can use the same atomic register actually to encode multiple graphs at the same time. Therefore, we can, in a sense, parallelize the data extraction feature of the method itself. This lends quite well to compensate with the inherent flaw of the neutral atom system, which is that they are relatively slow. So if you are given, for instance, thousands of graphs and you need 500 to 1,000 iterations per graph to extract a meaningful probability distribution, that very, very quickly adds up. So if your system is comparatively slow, you will still take a lot of time to train your method for practicality. Therefore, being able to parallelize and using the same atomic register and having multiple graph representations in the same atomic register can cut quite a lot of the execution time itself. More than that, if you design the pulse sequence efficiently, you can reduce drastically the number of shots, the number of iterations needed in order to generate a meaningful probability distribution. So you can cut from thousands to even hundreds if you're able to design more optimal pulse sequences. And what I wanted to showcase with this regard is an actual illustration, an actual experiment that has been recently carried out on our quantum computer itself. So in this specific notebook, this was used as a demonstration of the power of this tool. Let me put it on full screen so that it can be visualized correctly. So once again, to demonstrate the context itself for drug discovery, we are aiming at deploying small molecules. These are referred to as ligands that serve as your medication to be incorporated, to be integrated into a larger molecule that's visualized here, which is a protein. So these proteins are present in your system whenever you are sick, and these proteins are starting to misbehave. They have some undesired behavior and your medication is tasked to be integrated inside these proteins in order to fix the behavior, in order to repair the potential damage itself. For this reason, we have designed the quantum evolution kernel experiment in order to be able to encode graph structures in the atomic register itself. So what you can see here is encoding in total 2 different graph structures, 2 different molecules inside the atomic register, and then we send sequence of laser pulses to it in order to extract information. So on the right-hand side, you can see a visualization of the atomic register encoding the graph formulation, so the geometry of the molecule. On the left-hand side, you can see the associated probability distribution that's being formed. So the different measurements obtained for each of the bit strings based on the excitation that's observed for the system. And as you can see, for different graph structures, for different molecules, the probability distribution takes quite a different form. So we can use these extracted probability distributions as a footprint, as a representative of the graph of the molecule itself, to learn something, to be able to differentiate the different molecules, so the different graphs from each other. For this reason, for this very, very quick experiment, we have selected 3 different molecules as candidates from the lab rat toxicity experiments dataset that contains, I think, almost 25,000 different molecules investigated. So we have selected 5 different molecules, and what we are doing is that we are encoding each of these molecular structures inside the atomic register and exposing them to the same laser pulses. And you can see for the first molecule that has this this sequence of benzene rings in it, we have encoded it inside the quantum computer in the atomic register to represent the same geometry in a two-dimensional way. That's why we are considering only smaller molecules themselves, and we are exposing it to a specific sequence. So in this case, it's a single laser pulse that is used for a simplified interaction, and we repeat the same experiment for all the other selected molecules. So we encode the second molecule and expose it to a similar experiment to instill excitation between the atoms, to be able to capture the connections, to have some kind of representative of the graph structure of the molecular geometry of the molecule itself. Similarly, for the third molecule, we create the atomic register and extract information from it. And what we can see is once we have done this atomic encoding and carried out the experiment itself, we will obtain a probability distribution. In this case, it is measured by how many excitations we have observed. So instead of relying on the exact pattern of the zeros and ones themselves, we have already concatenated into that information into a much more compact footprint, which just measures how many atoms became excited, which gives this discrete probability distribution. And then we can use this as a tag to be used by our trained model to allocate whether for this geometric structure we expect a toxic or a non-toxic reaction. So we do this similarly for the other molecules as well and their representation in order to obtain the discrete probability representation. And what we can see is that even though that, for instance, molecules number 1 and molecule number 2 are quite different from a molecular or geometry perspective, their footprint, the probability distribution, has a similar structure. Therefore, the labels, the behavior associated to it from a machine learning perspective is predicted to be similar. Meanwhile, the third molecule, that's quite similar to the second one, from an architectural point of view, has quite a different shape in terms of probability distribution, and the machine learning tool is able to pick up on that and allocate a specific tag for a predicted behavior for this. Of course, this is a simplified example. I just wanted to showcase how it would work in practice. So the idea is to encode the molecule itself on the atomic register, then design pulse sequences. Potentially it can be quite complex, or in this case relatively simple, in order to extract some meaningful measures. These meaningful measures can be really the probability distribution of the actual bit strings, or it can also constitute something much more concatenated, such as the number of excitations in this case. And then you task a classical machine learning model into being trained, and then learning from these discrete probability distributions themselves in order to be able to predict or to be able to classify, in this case, all the while you haven't performed a single chemical computation. You really relied on the geometry of the molecules themselves in order to make these predictions. Yes, there was a question. So how can we encode the information about atoms and the number of bonds? So this is something that is not directly encoded into the method because in this encoding, what you are using is really just the geometric structure of the molecule. You are not interested in behavior on the orbital level. You are not interested in the exact way of the bonds. You are not interested in the different groups that are allocated to the molecules. So as you can see here, there are different, there is oxygen, hydrogen, different bonds represented in the molecule itself. However, what you've encoded was really just the geometry itself. And this already is sufficient enough to provide an initial information. Once again, this is a tool to do some pre-screening to try to identify potential candidates typically as fast as possible. So the least amount of information you need to generate something meaningful typically is the better. Nevertheless, there are techniques, there are ways to encode stronger and weaker bonds. So you can play around with the distance. So here you can see we encoded this the geometry of it by equidistant atoms. However, if you want to represent a stronger interaction, you have the possibility to move the atoms closer to each other. So the encoding itself, the geometric encoding itself, can give you access to manifest extra information that can be the strength of the bond or the type of the bond based on the distance. It can also be some considerations on how you manipulate the information if you want to have extra information on the different groups associated to the different nodes, especially for the free nodes as well. So there are ways to improve the system itself. What I wanted to illustrate is that in its simpler form already, it is something that can be quite efficient. Then, of course, you can complexify it by encoding additional information. Yeah, so question about the simulation and real experiments of the data. Yes, would it be more efficient to prioritize or optimize CAC for the types of graphs with smaller discrepancies to enhance overall performance, or would there be existing strategy to minimize these discrepancies for all graph types? Here, what is manifested in the two different numbers, so the standard and the size compensated, is the fact that you are really trying to create a generic or uniform method that works in all different classes of graphs. So be it small, loosely connected, or large and highly connected graphs as well. Typically, the more diverse the families of graphs you want to study with the same method, the more complicated it becomes to design an efficient experiment that provides reliable solutions for all these. What you would want to do is to create groups from your graphs and apply a specific optimized CAC versions for groups of graphs. So you refer to this as types of graphs in order to reduce the discrepancy, in order to diversify your model. That's a quite efficient strategy in order to enhance the overall performance. However, there is an intricate balance between how restrictive you are with the definition of types of graphs, because you don't want to make your experiment instance specific, because of course that could work for any kind of method. If you train your method on a single data set, then for that particular data point, it will work wonderfully, but for any other data point, it will have issues. It's a similar issue here, is that you want to create sufficient amount of diversity, meanwhile keeping to a specific type of graph structure in order to have your model sufficiently generic, but not too generic in order to have precision itself reduced. So there is quite a lot of optimization involved in trying to design a good enough architecture for the CAC representation. There is another consideration that is being manifested into the two values here, is that there is also the impact of noise. And noise can play a good, beneficial role as well as a disruptive role. At this stage, it's quite hard to distinguish in which case noise is having a positive effect, and in which case the noise is having a negative impact on the precision rates. In general, for quantum machine learning tools, it is generally viewed as a positive thing to have some kind of noise present in the system, because it can enhance considerations with respect to the optimization of the tool. So it can help avoid barren plateaus. It can help avoid some particular situations due to the naturally present noise in the system. This is, however, something that's more a particularity of NISQ type devices and NISQ type hardwares themselves. And with fault tolerance looming in the horizon, this is something that will become less prevalent. In any case, generally, it's viewed to be a positive thing without having an actual mathematical or scientific proof that it is positive to have noise in the system. So all these effects, the graph structure, presence or absence of the noise, contribute to the discrepancies you have observed. Are there any other questions? If not, so we have reached the end of what I wanted to share with you for today. Once again, thank you very much for everyone for your attention. I hope you managed to learn quite a few things, especially this second week, which was a bit more advanced session. Please do take a look at the different resources available online for most of the algorithmic implementation I've showed to you, especially on the optimization side. Everything is present on the Pulsar documentation that's available for everyone online. So you can see some more examples of different considerations, and you can also take a look at the cadence for the machine learning implementations that are quite more user-friendly than the Pulsar-based examples I've showed to you today. It was just to illustrate that even on the pulse-based level, you can do something meaningful. And don't forget to fill out the form that has been posted. I'm not sure, are there any specific instructions for that?